Also, in this video, we will be discussing pulse code modulation, and this video is mainly focused in calculation of transmission bandwidth of the pulse code modulation. So over here, I will not go into the deep of the PCM. That is, we will not derive any quantization, noise power, anything, because I am assuming that we all know that this video is mainly focused for calculation of transmission bandwidth, because many of the subscribers are requesting that we want videos on transmission bandwidth. Okay, so from this I will be starting the digital communication series, okay, whole, but I'm starting with this video, right? And let me know if it is helpful to you or not. So over here still I am briefing out what is pulse code modulation. So this is the message signal, right? So we can say this is the message signal xt, and this is low pass filter. This is done in order to band limit the message signal xt, that is in order to avoid the aliasing effect, okay, so that the signal is, our signal x of t is now band limited. This is the sample and hold circuit. So over here the message signal is being band limited, and then the sampling is being carried out by this sample and hold circuit. Let me write, this is sample and hold circuit, and after that the quantizer block will come. And what is the role of quantizer? The role of quantizer is to approximate the samples, that is over from the here what we will get, we will get samples, right? So this signal x of t being sampled at particular intervals, right, regular intervals with some appropriate sampling rate, these samples are being quantized. Because why the quantizer is needed? The quantizer is needed because there are infinite number of samples. Let's say the signal is our sinusoidal signal, right? So after sampling, okay, we will get signals samples like this, and in between we can have infinite number of samples, right? So in we can't represent infinite number of samples, okay, because it will require a large bandwidth, or we can say infinite number of bits in order to represent infinite number of samples. So for that purpose we are using quantizer, so that we can approximate the samples at particular value, so that we can represent the samples with finite number of bits, okay. So to represent samples using finite number of bits, right, this is the need of quantizer. And after the approximation, here comes the encoder, and it is nothing but our A to D converter, right? So this analog samples, okay, signal is obviously analog, this is a time domain, so this will convert into digital form. And one more thing, that this sampling and this encoder, right, both these things happens in a synchronization, okay. So proper synchronization must have to be managed, right? This, after this encoder there is one more block, which is nothing but, obviously this is A to D converter, so digital data is parallel, so we will need some parallel to serial converter, right? So this parallel to serial converter and this sample and hold circuit both work at same clock, okay, in synchronization. And after that we get our PCM output. So this is our PCM signal. The x of t is now being pulse code modulated, okay. This is the transmitter block diagram of pulse code modulation, right? So over here we will now directly jump to calculation of bandwidth, right? Obviously the transmission bandwidth. So transmission bandwidth of PCM, right? So all we have confusions in what is RB, what is TB, what is FS and all thing. So mostly this TS, TB, all these things creates confusion, right? So nothing okay, nothing is very much complex in this, okay, just stay tuned. So let me consider again the sinusoidal signal, right? And let's say this sinusoidal signal is being sampled and it is being quantized, right? And the quantizer level consists a range, a dynamic range from minus V to plus V volts, right? So by using any suitable quantizer, we have just quantized the signal. This is our message signal x of t, right, by sampling first and then quantizing. So we are left with this quantizer, okay. There will be some levels of the quantizers, right? So obviously there will be some suitable step size denoted by S, or we can say delta, right? So all these things is being done. Now what happens is that, let's say this signal is being sampled, and it is being sampled at the sampling rate fs. Okay, this is sampling rate. Now one very important thing that I need to discuss is that one sample can contains more than one bit. Don't think that one sample means one bit only. It can be of one bit, it can be of 2 bits, it can be of 3 bits also. Okay, so a sample that contains information can be of either 1 bit, 2 bit, or any kind of bits, right? So and obviously we will focus, or we will try to minimize the number of bits to represent the sample. Okay, and this is the topic of information theory, right? Obviously we will minimize because it will reduce the cost. Who needs more cost, right? So obviously we will try to minimize. So all those stuffs are discussed in information theory. So the sample can consist of more than 1 bit also. 2 bit sample is also there, 3 bit sample. So it depends, right? So this major confusion or major wrong impression I need to clear first. Now coming back to this, let's say this signal is being sampled, okay, and these are the samples. Let's say for simplicity consider 4 samples, right? This is sample 1, this is sample 2, third and fourth one, right? So these are the samples, and obviously it is being sampled at sampling rate of fs, or we can say the uh, spacing between them will be ts. Spacing between the samples, consecutive samples, will be ts. That is, they are sampled at a time interval every ts seconds. That is, they are sampled after every ts seconds, right? So obviously the time interval between these two samples is will be ts, right? Any time interval between two consecutive samples will be ts. So I am just writing for one. So this is ts, and which is nothing but 1 upon fs, right? So this fs is nothing but 1 by ts. We can write like this. This fs equals to 1 by ts. So this is ts equals to 1 by fs. Now important point, that this sample, as I told, that this sample, okay, this sample s1, s2, anything can be of more than 1 byte. It can be of one also, or one or more than one, right? So let's assume that these samples in general case are of n bit. Okay, that is, we are using over here a n bit encoder, right? So over here we are using n number of bits to represent one sample. Clear? So what will be the signaling rate? That is, let me just zoom this s1, that is one sample. This one sample consists of, let's say this is 1 bit, right? Let's say 2 bits, one and this one, both should be of same interval, right? Let's say 3 bits over here, right? So this is 1 bit, right? This is another bit, this is another bit. This sample is made up of 3 bits, right? So this is 1 bit, this is second one, and this is third one. Okay, this sample s1 is made up of 3 bits. So the distance, okay, this time interval is denoted by tb. This is called tb, right? Bit duration, we can say. That is, the transmission of this bit requires tb seconds, right? So this tb seconds can be written in frequency domain as 1 upon rb, right? Which is nothing but bit frequency, right? Or we can say another name, signaling rate, right? So our signaling rate is given by RB, which is nothing but 1 upon TB. Sorry, this is not called signaling rate, this is called bit rate. Okay, this is the duration of one bit, so this will be called bit rate. I'm sorry for this. This is called bit rate, right? Bit frequency, or we can say bit frequency, or we can say bit rate, right? And is being denoted by RB. It simply represents number of bits per second. RB is nothing but number of bits per second, and which is denoted by 1 by TB, where TB is what? TB is duration of one single bit, either 0 or 1 or anything. The TB represents the duration of a single bit, right? Now let's move ahead. That this one sample consists of this 3 bits and each of duration TB. So this S1 consists of 3 bits, which is nothing but this, and each of duration TB, right? So for a general case, that it will be let us consider general case of n bit. So obviously this interval TS should always be greater than or equal to n times TB, because this is 1 TB, right? This is TB, this distance is also TB, this is also TB. So for over here, just for example purpose, I have considered only 3 bits, but in general we are discussing about a n bit, right? So this TS should be greater than or equals to n times TB, because if it is less, then there will be overlapping between two samples, and which will lead to error, right? So for that purpose, this equality must hold. This inequality is very much important. So don't go further in the video if you won't get how this equality came, right? So now in frequency, in terms of frequency, TS is nothing but 1 upon Fs, which is our sampling frequency, should be greater than or equals to n times TB is nothing but 1 by RB. So it can be said that RB should be greater than or equals to nFs, or we can say we must have minimum bit rate of nFs. If it is greater than nFs, it will be okay, but minimum nFs bit rate is must, right? So I hope this is clear. This equation is very much important. Let's say it equation number 1. Okay, let me finish on this page only. So over here, let's say this is equation number 1, right? So this inequality, okay, this RB is called the bit frequency, or we can say number of bits per second. Now what we want, so now pay attention very well. We concluded RB equals to nFs, and this is equation number 1. So writing it again, sorry, RB equals to nFs, right? So what is Fs? We know that Fs is the sampling frequency of the message signal, right? Whatever the message signal xt was there, that is over here, right? The message signal is being sampled at, this sample and hold signal is being sampled at Fs frequency, right? Sampling frequency. So this is the sampling frequency of message signal, right? And what is nFs? nFs is nothing but sampling frequency of PCM signal, right? Mind the difference. Fs is just the sampling frequency of the message signal x of t, right? The x of t, this one, this is x of t. But what is nFs? The nFs is nothing but the bit rate or bit duration, and which is nothing but the bit rate, right? And which is nothing but the sampling frequency of the whole PCM signal, that is this signal. This samples S1, S2, this is whole PCM signal, this is whole, okay, one PCM signal, right, which is to be transmitted. So this is the sampling frequency. This whole n into Fs is nothing but the sampling frequency of the PCM signal, correct? Please don't get confused. So Now let f beta is bandwidth, or let's simply write let bw, let denote by bw, that let bw is the bandwidth of PCM signal, right? So what will be the sampling frequency of the signal having bandwidth bw? Obviously by the Nyquist criteria it will be twice bw, right? So this is nothing but the sampling frequency of the PCM signal, and we know the sampling frequency of PCM signal is what? N times fs, right? So it is nothing but n times fs. So what answer of our bandwidth is? Bandwidth is nothing but nfs by 2, and it is found in many books. Okay, directly that is written like bandwidth is of PCM signal is nothing but nfs by 2, right? So here comes the derivation of the transmission bandwidth of the PCM signal, that is for PCM, that is pulse code modulation. Okay, we need the minimum bandwidth of nfs by 2, right? Now let me summarize all those stuff. So n is nothing but number of bits per word, that is how many bits we are using, right? Fs is the sampling frequency of the message signal. Okay, so sampling frequency of xt, right? And bw is the bandwidth of the PCM signal. So I hope it is clear, right? Let me know in the comment section if there is any sort of confusion. Okay, I am repeating it again, that what I am talking about, that is simply we got RBS and FS, and this Fs was the sampling frequency of the message signal x of t only, right? But this NFS was the sampling frequency of the whole PCM signal which we got, which we will be using for transmission of the data, right? So this is the sampling frequency of whole PCM signal, right? If we are using 2 bits per word, then it is twice fs, 3 bits then thrice fs. It depends. We are generalizing over here by taking n bits, right? So now we suppose that the bandwidth of our PCM signal is bw. So as per the Nyquist criteria, what is the sampling frequency of that? It is twice of bw, and twice of bw must be equal to this nfs. So we got bandwidth as nfs by 2, right? So this is the transmission bandwidth. Mind that this is the transmission bandwidth required for PCM transmission, right? If someone asks what is the message bandwidth, right? So obviously we know that message bandwidth is nothing but the sampling frequency of message signal xt is nothing but only fs, right? It is not nfs. Nfs is for whole PCM signal. Okay, this is the only point which is to be taken care of. So the bandwidth of only message signal, okay, or we can say message signal bandwidth, will be given by this n will not be there, only fs will be there, just fs by 2. So these are the two important points which is to be taken care of. Thank you.